So in the last class, we had discussed about the overall family of smart materials, how these smart materials can be selected for a particular application, and what are the different process parameters which are involved with reference to smart materials. In fact, we had a discussion about the shape memory alloys, about the family of shape memory alloys, what are the different parameters which are involved with reference to shape memory alloys. This video will give you a better clarity like how a shape memory alloy work, where there is a spring there which is tied to a weight. Because of the weight, it is getting deformed. When I try to apply an electrical biasing to it, it comes back to its original shape. And similar responses are happening over here. Like when we try to elongate the shape memory alloy spring and put it in a hot water condition, it comes back to its original shape. Now the mechanism behind this, which we had seen, is a kind of a austenite to martensite shift. And with reference to the austenite to martensite transformation, we get a kind of a actuation which exhibits in this particular shape memory alloy structures. That's how we are involved in micromanipulation of shape memory alloy structures for different applications. Now let us see the overall types of shape memory alloy effect which exhibits, because based on the type of these shape memory effect, appropriately we can design our actuator for micro robotic applications. So if I try to classify the type of shape memory effect, there are two types of shape memory effects are demonstrated. It is called as one-way shape memory effect, and the other one is called as a two-way shape memory effect. In the case of a one-way shape memory effect, let us consider a shape A is straight. When I am trying to supply a heat to it, it takes a shape B. However, when I try to quench it, it will be in the same state, that is martensite, austenite, martensite. That is, it won't come back to its original shape. So it's a kind of a one-time deformation which happens. However, in the case of a two-way shape memory effect, let us consider a shape A, which is initially in the martensite phase. Now when I try to heat it, it takes up a shape B, which is a form of a austenite phase. On cooling, it comes back to its shape, which is again a kind of a martensite phase. This happens without any kind of external loading. So this effect is called as a two-way effect. That is, let us consider a cantilever. So the cantilever is loaded. Okay, so the cantilever is deformed. When I try to supply heat to it, it remembers its shape and it comes back to its state. This is called as a one-way actuation. In the case of a two-way actuation, so it is in shape A, shape B and shape A. So this is happening by a two-way effect, that is, it from position A to position B and position B to position A. This is called as a two-way shape memory effect. Now how to program this material for this particular shape memory effect, or to train the material, or how to make this material remember its shape. Okay, for that there are different types of mechanism which exist. However, for that we need to have a fundamental understanding of the phase transformation which is getting exhibited over here. Like if you closely observe in the case of a shape memory alloy, so we have seen it is a switching behavior between the austenite phase and the martensite phase. So let us take an example. So the main device over here is, I have close to around 0.25 mm thick shape memory alloy plate. So initially the shape memory alloy plate is in the initial shape. Now it needs to remember this particular shape. So what we are trying to do is, this is on an initial shape. If I want to train it to a particular shape, so I prepare a fixture in such a way that inside this fixture I apply a loading to it. Then in order to make the shape remember, so basically this is called as programming of the material. What we try to do is, so we try to go for several heating cycles. That is, we deform it in this shape, put it inside a muffled furnace, heat it to 500 to 550 degrees Celsius, which is almost close to the martensite phase, and then I quench it in an ice water or a liquid nitrogen conditions, so that it comes back to the austenite phase. So this switching between the martensite and the austenite happens in such a way that you get a kind of a closed structure or a kind of a deformed structure what we are looking for. So as far as in this process is called as a shape setting. However, with reference to robotic perspective point of view, we call it as programming of of material. Sorry. So why do we call it as programming? Because so that we are giving a shape, or we are setting the shape based on the requirement, so that appropriately it gets actuated. Now you may ask me a question. So in case if it is this is a kind of a one-way training, what happens to the two-way training? So first I need to get a naive material. So from the naive material I may need to train it for a one-way training, and then what should I need to do is, after training it for a one-way training with reference to a particular shape setting, now I need to deform it to the next level and I need to repeat the cycles. So what happens is, the initial naive training will be completely eradicated from the memory of the material, and then the switching between the one-way training and the one-way actuation and the two-way actuation happens. So that is something like, if this is like this with a particular angle, and this is, suppose this is like this, so I need to switch between here and here from the material which is flat. So first I try to train with geometry A, then from geometry A I train the material to geometry B. So this I will be loading and unloading, that is I will be switching these two mechanisms to get a kind of a structure. Okay. In fact, I would like to show you a video over here which talks about the actuation of it. So this is a simple actuation of a nickel titanium. That is why it is getting actuated even with a lighter. So the estimated temperature is close to around 80 to 110 degrees Celsius, which we call it as a actuation temperature. So which is capable enough in actuating these shape memory alloys for different functional applications. Like for example, in this particular case, these kind of systems can be efficiently used for some kind of bimetallic contacts. However, if I want to go for a continuous actuation, then there is a possibility that I can go for a Joule heating to create such kind of structures. Now, as far as these types of shape memory alloys are concerned, so we have already seen that these shape memory alloys are either nitinol based. So as far as these nitinol based shape memory alloy structures are concerned, they have a high recovery strain, so up to around 8%. And most important point is, as far as these shape memory alloy structures are concerned, these shape memory alloy structures has an excellent biocompatibility. So that is the reason it has a potential application towards biomimicking related robots, and it can be efficiently used for biomedical related device like stents, orthodontic wires, etc. Okay. So as far as in this stents related applications, so it has a capability to immerse and then it can be actuated. Then we have a copper based shape memory alloys. So as far as this copper based shape memory alloys are concerned, so Cu-Al-Ni combination, Cu-Zn-Al combination are some of the kinds of shape memory alloy structures which are being exhibited here for effectively for actuation related application. So as discussed, one of the key point is, like, it has a lower transformation, and since the lower transformation behavior is considered to be one of the advantage of using copper based shape memory alloy structures, especially so whenever we are developing a micro robot for a lower temperature transformation, this combination is considered to be a promising combination for a kind of cryogenic related application. Next we have the FeMnSi or FeNiCO(Ti) ion based alloys. So as far as in this ion based alloys are concerned, these are called as magnetic, these has a magnetic shape memory property, and in fact it is of low cost compared to nickel titanium. So it has a potential application towards structural related characteristics. In fact, in a technical term, we call these shape memory alloys a kind of a passive shape memory alloys. So these passive shape memory alloys are capable enough for pseudoelastic related application. However, for an actuator perspective point of view, it has its own limitations because of the response time. Now, when I try to talk about the characteristics of shape memory alloy, these shape memory alloy has a good mechanical properties, like basically it has a high recovery stress, a large recoverable strain. It also has a good fatigue resistance, and as discussed with respect to biocompatibility point of view, so NATI is widely used in medical applications. Now, the one of the major aspect which comes into picture is the manufacturing of shape memory alloy. So, when we try to take this manufacturing perspective point of view, since these shape memory alloys are highly responsive to heat, in fact, I would say that it is highly sensitive to heat. Even a slight variation in the structure will result in a kind of a different material. Like for example, if I have a combination of nickel titanium Cu, so let us consider this is a ternary alloy. Ni I am adding close to around 45%, titanium around 45% and 10% of copper. Even if there is a minor variation is there, this may result in shifting of the shape memory alloy to a different level. Second thing is, let us consider I have a shape memory alloy rod, shape memory alloy sheet. Okay, so these shape memory alloy sheet, say if I want to machine it, so of course I will be going for a drilling process. It will be very difficult for me to drill using a drilling process, because whatever heat which is getting generated, so based on the heat which is getting generated, it tries to get deformed and it may have its own impact. So that is why normally we prefer to go for a origami-based machining, so that there is less amount of heat transformation which happens, and appropriately we try to create the features. Now, commercially, when you try to buy these shape memory alloy structures, so these shape memory alloy structures are commercially available in the form of wire form, powder form, sheet, plates or rods. Okay. So, in the wire form, of course it can be in different diameters. Powder form perspective point of view, many cases like Ni is taken separately, titanium is taken separately, and it is being appropriately ball milled to get the structure. Then in the form of sheets, like we can get a thin sheets of from 0.1 mm to a higher order. Plates, we can go for a thick plates also. In certain cases, we also get it in the form of a rod, which means that, and most of the commercially available structures, these kind of shape memory alloys, which has a higher wherever there is a bulk manufacturing requirements are there, appropriately these things are taken. In fact, sometimes shape memory alloys we get it in the form of a springs also. So which has a potential application towards like which has a potential application towards actuator development, and in certain cases it is also used for certain amount of sensor development. Now, as far as traditional perspective point of view, as we have seen, so these structures are basically melted in a vacuum to prevent the oxidation, and then after melting, so what happens is like either it is going for a casting in the form of an ingot, and in certain cases it also goes for a heat treatment to set the transformation process. Like forming of the shape memory alloys is a challenging task, so forming process like rolling can be employed. However, now recently there are wide variety of research focusing upon taking up additive manufacturing route as one of a promising route for this shape memory alloy fabrication. In fact, a wire arc based additive manufacturing route is considered to be one of the promising route, where since we have a wire form, so the wire form is fed. In case if you need to add an intermetallics, so appropriately you can use a separate wire feeder, and then we can feed the powder, we can create the structure based on our requirement. This is one way. Second way is like, since it is in the form of a sheet, we can use a kind of a friction stir based additive manufacturing to prepare such kind of structures for a thicker sections, etc. And then a powder metallurgical route is one way through which like people are developing bulk structures. However, DED process, direct energy deposition based techniques, can also be deployed through either it might be a powder bed or it might be a nozzle base. So through which we can just have a multiple powders. These multiple powders coagulate and then it creates a structure based on our requirement. So of course, additive manufacturing is considered to be a promising for creating such kind of complex shape-based shape memory alloys based on our requirement. However, like here, one of the major challenge which exists over here is training these shape memory alloys based on our capability. So, like what people used to do is, whenever they try to go for an additive route, the whatever shape setting which has been made initially is considered to be the original shape of the particular material. Now, a kind of a fixtures can be deployed to have a kind of a series training, so that with this training we can have an adaptable structures what we are looking for. Now, as far as shape memory alloy perspective point of view, this is one good example where a shape memory alloy wire, it's a kind of, it is initially in the martensite phase, is being inserted inside the artery, and the wire form filter as it when the wire gets this one, so it gets the body gets warm, and because of that certain amount of clots or trapped are completely removed from this particular process. So this is a kind of mechanism which is being deployed for removing a kind of SMA clot based structures. SMA clot. In fact, the same, almost the similar technology is deployed for inserting a SMA based stent, and when we try to actuate it, this stent gets enlarged and appropriately it can be used. Similar to this, based on the NITI springs, we can use for developing a SMA actuated robot. So like the loading can be through the concerned link, and then by applying a kind of actuation through this, by connecting it with the appropriate wires, by giving an joule heating to this system, so we can have a kind of a manipulation. Recently, there are some reports where people use a laser for heating such kind of shape memory alloy structures. So appropriately by selective heating, so what happens is there will be a kind of a actuation which happens. These actuations are capable enough in such a way that it can be used for actuating the shape memory alloy based on the characteristics. Now let us see some of the key applications of shape memory alloys as far as micro robotic perspective point of view. On a micro robotic perspective point of view, shape memory alloys are used as a kind of a propulsion system, or shape memory alloy are used as a kind of a supporting structure system. Like this is a kind of a supporting structure. By actuating it, we can have a kind of a displacement which exhibits over here, and this is a kind of a propulsion mechanism. So in this propulsion mechanism, there is a kind of a shape memory alloy spring is integrated into it. So by actuating it, we can have a kind of a actuation which almost gives a biomimicking capability to the structure. Now this is a kind of a bio-inspired SMA bimorph and a bio-inspired a kind of an origami robot. So in this particular aspect, in order to develop it in the form of if we need to develop it on a micron level, so one of the key aspect is, since we have a shape memory alloy in the form of a wire form, we can integrate the shape memory alloy wires along with a kind of a composite structure or a polyimide structure based on our requirement. For instance, let us take a composite structure. This composite structure is integrated with the shape memory alloy wire. So in order to give an appropriate program to it, for example, if I am looking for a actuation something like this, so one option what I can do is I can give a kind of training to the SMA wire by straining the SMA wire from 2 to 4%. So what happens is, when I am straining a wire up to 4%, so appropriately what happens is, over these strained wires, so we have a kind of a PDMS structure and a a composite structure which is being integrated into it. So what happens is, when you try to actuate this shape memory alloy structure, these composite structures will try to get deflect and then it tries to come back. Okay. So like in this particular case, we have a polyamide. This polyamide is integrated with a micron SMA wire. So these SMA wires are integrated with this polyamide composite structures, and these SMA wires are strained up to 2%, so that this 2% will be the kind of a programming for this particular shape memory alloy, so that the shape memory alloy gets actuated and there will be a kind of a displacement which exhibits over here. So based on the displacement or based on the frequency, ideally your displacement and the frequencies are correlated to the straining of the SMA wire. Once the SMA wires are strained, appropriately composite is being encapsulated on this, or in certain cases what people do is people strain the SMA wire and then they try to encapsulate it. Now let us, so these are some kind of SMA based composite structures, so which is being incorporated. So it's a kind of SMA based origami robot which is actuated using an underwater application. Of course, we will discuss more about this in the biomimicking module. Now let me just take a simple example where, or a simple case study where an SMA embedded structure is fabricated with a PDMS. So PDMS is a kind of a jelly kind of structure. It's a kind of a soft structure which is used for kind of biomimicking related applications, or it is also used for soft robotic applications, etc. So first thing is, we are trying to print the mold using a CAD, and then these molds are 3D printed, and inside this 3D printed structure, so we are trying to integrate a SMA wire. So over this SMA wire there is a mold which is being kept, and these SMA wires are strained from 2 to 5%. So over this 2 to 5%, the PDMS structure is being laid, and then the PDMS is skewed for an appropriate composition matrix. So what we are trying to do is, so there is a mixing of a PDMS structure, and finally it's a kind of a kind of a SMA integrated PDMS layer which you could observe over here. Now this is a kind of a study which is evolved to investigate the actuation behavior of these shape memory alloy structures. So basically this is a kind of a structure where the SMA wires are integrated into it, and the actuation is done through an electrical biasing. So it's a kind of a joule heating which is done. So we could see that there is a kind of a temperature rise which increases with reference to the applied current. So as and when once the current increase, appropriately the temperature increase, which will result in the actuation. Now let us see a small gripper which is fabricated using a kind of a SMA based biomorph. So in this is a kind of a PDMS structure. This is a kind of an SMA which is integrated into this PDMS structure. So where we could see like these structures are trained with different percentage, like this is 2%, 4% and 6% strain. So based on the straining impact, so appropriately it has a capability towards load carrying capacity. So, and most important thing is, since it is being strained, it has an actuation in this particular direction, and when you try to fit it up, so appropriately it holds it and it retains it for a particular time. So you could keenly observe up to 2.5 kg load, 2.5 grams load it could load, and this is up to 3.5 grams with a 4% strain which is embedded over here, and up to 7 grams where a kind of a load can be actuated in it. Now we based on the gripping arrangement, so appropriately we can use this system for different application. So to summarize, so we had discussed about the shape setting characteristics in a shape memory alloy. So in the case of a shape setting characteristics, we have discussed about the one-way shape memory effect and the two-way shape memory effect. how a one-way that is which is more required for programming the shape memory alloys for different robotic as well as micro robotic related applications. So when we if we need to program it appropriately, we may need to have a kind of a manipulation in the memory of the material. So for that, certain methodologies are followed. Since it works on the austenite to martensite transformation, a die can be prepared and appropriately it can be deployed in a kind of a hot and a cold conditions, and then we can observe or we can train the material. Shape setting can be evolved out of it. So as far as one-way shape memory effect is concerned, it is switching between the nave to the shape. As far as two-way shape memory is concerned, it is switching between two shape setting domain, so that it can be used as a kind of a actuator, and you can also use it for a frequency based system. So this is a kind of a shape setting procedures which are being followed over here, and this is the actual actuation of a shape memory alloy thin sheet which is being actuated with a temperature of around 80 to 110 degrees Celsius. So we had discussed about the different types of shape memory alloy structures and its properties. So we also had a discussion about this manufacturing of this shape memory alloys. So with reference to manufacturing, so as mentioned, it is highly sensitive to temperature. So appropriately manufacturing routes should be deployed, and by deploying this manufacturing routes, so we can employ it for different applications. So this is one practical application where shape memory alloy structures are used for removing the blood clot in a structure. So there is a kind of a tube kind of structure through which shape memory alloy wires are incorporated, and then by giving an appropriate actuation to it, you can manipulate the beam for our requirement. And this is a kind of an SMA actuated robot. So where there is a base with nickel titanium based springs which are being deployed into it. So by actuating it at different conditions, we can see a kind of a kind of actuation which persists over here, and these actuations are capable enough in such a way that it is used for holding or manipulating the structures for different applications. Now, since these materials has a capability towards biomimicking, it has a potential applications for different robotic structures for biomimicking related applications. So it takes care of the structural and it takes care of the propulsion, and these are some kind of biomimicking based robots. So I had given you an idea about how SMA integrated composite structures are fabricated, SMA integrated polyamide structures are fabricated, how these structures are being incorporated into the system, and this is the overview of the performance of this shape memory alloy integrated PDMS structure, which is used for as a gripper over here. So a kind of a manipulation which exists, which takes care of the loading and the unloading of the systems. Okay, now we will discuss about one of the important case study where shape memory alloy based micro actuators has been developed for a kind of optomechatronic application. Basically, we have developed a small shape memory alloy thin film based Stewart platform, a parallel manipulator for beam steering related application. So that case study we will discuss in the upcoming class.